Good morning, everybody. Today, I want to talk about the basic problems of evolutionary biology, which is the reconstruction of evolutionary history based on molecular or morphological data. But the basic point is not empirical studies, because there are many unsolved philosophical or epistemological problems. So, let's go. Understand biodiversity is a very important point for today's environmental pollution problem or any other worldwide problems. But there are many theoretical problems to be solved because we have many known or unknown organisms of the extended world, but this is a species scape which was drawn in about 15 years ago. This is another kind of manner of the biological world. This picture is drawn according to the species numbers. So there are many arthropod species, or there are few vertebrate species. But in this case, we must consider some fundamental problems. That is, how to organize narrative biodiversity. In this case, we have a general science which is called systematics. Systematics, in general, is a science of systematization. But we have two different kinds of criteria for describing biodiversity, because there are science of taxonomy. Taxonomy is categorization by similarity or dissimilarity among organisms. But we have another kind of science, which is called phylogenics, which is based on the inference of history of organisms. So in this case, we must consider what is the difference between taxonomy and phylogenics. Okay. About 150 years ago, the philosopher William Fuller, which is the famous philosopher in England, he made classification of sciences. In this science classification list, he distinguished between classificatory science on the one hand, which is science for classifying object according to its singularity. On the other hand, he made a new word, pathological science, which is science of historical causation. He distinguished between classifying and historical causation. This is a very important point, because pathological science is now an obsolete word, so it's not at all, it's not used at all. In this case, the most important point is what is the basic distinction between taxonomy and phylogenics. And my opinion is that both sciences are working on the same object, say organisms or lung disease or manuscript. On the other hand, they work with different purpose and method. This is the schematic diagram of phylogenetic tree. We have a common ancestor at the root of this tree, and we have several kinds of descendants. The time axis runs from below to the upper of these figures. And if we cut off this phylogenetic tree at one time dimension, we have classificatory pattern of this figure, say, in this case, this figure shows several patterns of classificatory groups, which is called task. So in this case, we want to consider between the relationship, say, this phylogenetic tree and this taxonomy map. Last summer, I went to Mexico to attend a meeting, and this city, Oaxaca, the South Mexico, has a very important and brilliant church. This is Santo Domingo Church. And entering this main gate, we can find a very big trees. This tree, which is called the Tree of Life in this church, which is genealogy of Christian saints, which contribute to the expansion of Christianity in medieval Mexico. So in this case, we have, say, ancestors and many descendants from this, according to this tree. But I'm not a Christian about this, so I must go to the biological world. This is a figure of Eros Haeckel's phylogenetic tree. So in this case, Eros Haeckel drew this phylogenetic tree based on some empirical data and his imagination. But basic structure of this tree is simple, because in this phylogenetic tree, we have an ancestor and several descendants. But the most important and difficult problem is how to estimate from this descendant knowledge and to ancestors. Say how to infer from descendant to its common ancestor. This is the best important point of the phylogenetic research. Okay, we have several kinds of figures which depict the basic structure of phylogenetic trees. In this case, ancestral population divided into descendant population according to some geological or biological event. In this case, we have an ancestor A, which is divided into descendant B and C. But our human societies have several phylogenetic trees, which is called genealogical trees, because in human societies we have more than 1 millennia. We have several kinds of phylogenetic trees of our own societies. Say this is the most important point for our understanding of phylogenetic relations. This figure is the oldest figure of genealogical trees, which is drawn in 9th centuries. Okay, this is the pictures of phylogenetic trees. We have many examples of phylogenetic trees in human societies, and not only human societies, but also several other kinds of objects have its own phylogeny. Say, this is the trees of knowledge. This is from 13th centuries philosophers, Raymond's rules, and this is the encyclopedic tree of knowledge in 18th centuries. Next is the tree of art. We have many kinds of contemporary art, but they constitute a phylogenetic tree in this case. This is the avant-garde tree of art. Next, we have, yes, tree of technology. So in this case, we have several kinds of phylogenetic trees which extend biological entities to non-biological entities. One of the most famous examples of non-biological phylogenetics is say the Canterbury Tales phylogeny. Medieval Canterbury Tales had many variants, so their mutual relationship can be drawn using phylogenetic trees. This is the Nature correspondence, which is published about 10 years ago. So the most important point, such manuscript phylogeny, is this diagram was developed according to biological principles. So biological evolution and non-biological evolution have many parallel characteristics in common. So we have some philosophical problems underlying this phylogenetic research. This book, which was written in 1904, so the author Taka proposed a new word he calls historiographic science. What is historiographic science? His examples are for, say, biblical criticism, say, classical biology, and comparative linguistics, and evolutionary biology. Okay, these domains are different, say, science or non-science regions, but all these historiographic science has some characteristic in common. Because the common nature of historiographic science is two. First, similar effects that preserve the information about the common cause or causes. So the first keyword is common cause. Next, the probable reconstruction of the intervening stages between common cause or causes and similar effects. So we have two keywords which characterize historiographic science. One is common cause. Next is reconstruction. So here, we have reached the next stage of our research because these two keywords, common cause and reconstruction, lead to abductive inference. This abductive inference, very important point to understand the basic nature of historiographic science. Charles Sanders Peirce proposed abductive inference as a third logical inference format. He distinguished between three kinds of inference, say, deduction, induction, and abduction. And here, inferring history is a kind of abductive inference. Now, abductive inference has four-stage procedure. First, B is a collection of data. Second, H is spread B. Third, H is the best among other alternative hypotheses. Then choose H. So abductive inference is the inference to the best explanation. Okay, this is a very good point for historical research. We can find the best hypothesis based on several sources of data. But here is practical difficulties concerning abductive inference in phylogenic reconstruction. This is the diagram to explain the abductive inference. This is the problem for phylogenic reconstruction in biological world. Say, we have a kind of data which is drawn from the unknown tree of life. So for this data, we have several alternative hypotheses. In this case, we have three phylogenic trees, say tree 1, tree 2, and tree 3. Our problem is how to distinguish between these alternative hypotheses as relative to this data. There are many kinds of optimality criteria to distinguish between different kinds of trees, but add some simplistic criteria, which is the maximum parsimony method in phylogenetic analysis. In this case, the best tree is a tree which minimizes the total number of character changes for this data. So in this case, we can calculate the parsimony scores for each tree. So then we can choose which is the best tree for this entire set of possible trees. But here is very important, difficult problem, because if we increase the number of taxa, number of objects for this reconstruction program, the number of possible trees exploded in this case. So for 1 or 2 or 3 number, say we have only a few possible trees. But if we have 10 species, we have, say, it's large numbers and more terminal numbers. I can count these numbers. So this is a very practical problem, because any other optimization problems, if we have one optimality criterion, we want to find which is the best solution for all, in this case, tree space. And our purpose is to find the global optimum for this entire search space. But we can't easily find the best trees for this tree space in the practical size of this set. In our era of increasing data set, we have, in some cases, say 100 or 200 terminal taxa, so we can't find easily which is the best solution, which is the best tree for such large data set. Okay. So we must understand the basic nature of phylogenetic research, because phylogenetics is, of course, established field of science. But now phylogenetics are based on 3 different kinds of roots. Say, evolutionary biology is the first root, and second is statistics. Okay, all data has some degrees of variation, so we must statistical error of phylogenetic tree. And third, we must the basic structure of phylogenetic tree is graph. So applied graph theory or discrete mathematics is the third root for phylogenetic analysis. But we must broaden this science work, because another kind of science also related to the phylogenetics and its related sciences, because historical science and cognitive science and philosophy of biology all connected to phylogenetic research program. Now, okay. The tree of life, which is a kind of mandala, as Okanai says. So the tree of life is a final purpose of all evolutionary biologists. In this case, the tree of life includes, say, birds or shrimps or plants or any other kinds of organisms at each part. And now, our grand purpose for all phylogenetic biologists is to reconstruct the total entire tree of life based on various sources of data. So we can now reach, we must solve some practical problems to reach this grand purpose. Finally, I want to talk about several famous persons in the history of phylogenetic or evolutionary biology. Okay, Phylogenic, he is a famous geneticist, and he is a construct of evolutionary synthesis in 1940 years. And he said in an article, say, nothing in biology makes sense except in the life of evolution. So this is a very famous passage, so many cited in other papers. But prior to Phylogenic, we had another message. Oh, he's Johann Sebastian Bach. His newly discovered cantata in 1905. The title is very impressive because he titled this cantata as "Alles mit Gott und nichts ohne ihn." Literally, everything is God and nothing without Him. Contemporary evolutionary biologist bases his research on some phylogenetic tree. So in this case, let's replace this word God to phylogenetic tree. Its German wording is here. Alles mit Stammbaum und nichts ohne ihn. Literally, yes, everything is the tree of life and nothing without Him. Thank you very much.
Thank you very much. Now the session is open for discussion, question. Please.
Hello, good morning. It might be a good idea for us to give our names and where we're from. That way we can get to know each other. I'm Dave Deemer at UC Santa Cruz. I enjoyed your talk. I have looked at these various trees and carried them from Haeckel's tree to, say, the Five Kingdoms tree to the three-domain tree at Barbosa. And so trees evolve along with scientific history. And I wonder if you'd comment on whether Haeckel's tree was the best tree at the time, or did he compare alternative trees? And what about the Five Kingdoms tree, and what about the Three Domains tree? Yeah. How do these things evolve? What are the forces that cause evolution of the trees?
Yeah, okay. That's a very important question. But in this case, abductive inference gives not always gives the true solution. Okay, so abduction is the mean to find the best solution, not exactly the true solution. But our main purpose to phylogenetic analysis is to find the best solution at the present status of data. So that's all.
Okay, right.
You are talking about tree of biology,
Yeah.
but I would like to know exactly what kind of data have you examined to draw the tree, phylogeny tree?
Yeah, okay. So in biology, say morphological characteristics or contemporary molecular phylogenetic sequence is the best data source for phylogenetic estimation. But historical linguistics or my script schemata have different kinds of data source.
So depending on the raw data,
Yeah.
different kind of trees may be appearing.
Yes.
So how can you then choose which one is best besides statistical methods?
I say optimality criteria.
Yeah, yes, you said.
Yes. Okay. There are many kinds of, or several kinds of optimality criteria because, say, maximum person mean or maximum likelihood or Bayesian posterior probability has a candidate for such optimality criteria. But all these criteria may be united into one simplistic criterion, say in this case, FDA principle, or any other kind of general personality criteria. Maybe unite such all other automatic criteria used in biological research in natural or social sciences.
But to me, such criterion is only standing on non-biological concepts. It's just like mathematics. So,
Yes.
Is it possible to understand the real difference between living organism and non-living matter based on this kind of research?
Of course, choosing among phylogenetic trees may be statistical or mathematical, but the basic point is biological information is vital in choosing which characters to use in phylogenetic estimation. Yeah.
Okay, thank you so much.
Okay. Now we have still more than 20 minutes for discussion, so please, yeah. Okay.
I'm Vidyanand Najjudaya from the Indian Institute of Science in Bangalore. I enjoyed your talk very much. I had a question about the phylogenetic tree which you showed for the Canterbury tails. Now, in biology, there is one principle we use in building trees, which is that of ancestor-descendant relationships. But it seems to me that in situations of this kind, I'm not familiar with the Canterbury tales, but people have tried similar exercises with a mythological story in India called the Ramayana. And the Ramayana is believed to exist in more than 100 versions. And there are attempts to find out whether there's any relationship between these versions of phylogeny, and if so, what. But the problem is that there's a great deal of horizontal transmission of information in the history of the Ramayana, which I imagine would be the case in most similar situations. How does one build a tree then?
Okay. In my talk, I always gave three structures to analyzing biological diversity, but in fact, we must estimate not tree, but network structures for analyzing phylogenetic relations. Because, as you say, there may be some hybrid or reticulations between phylogenetic branches. But estimating phylogenetic networks is much more difficult than analyzing trees, because computational difficulties to calculate the best solution for networks is perhaps NP hard or NP complete than estimating for trees. That is the practical problem.
Okay. Yeah.
I'm Jun Otsuka from Philosophy Department of Kyoto University. Thank you very much for the very interesting talk. Well, I was interested in your reconstruction of tree of life using the principle of parsimony. Well, parsimony is a principle based on correlation, and correlation is not same as a causation. And I think this is a main motivation for the decent development of causal inference, such as de-separation of Bayesian networks, some kind of these stuff. So I was wondering whether you have such method in phylogenetics, in such kind of method, sorry, phylogenetics as a causal inference, which is not same as parsimony.
Very difficult problem, because yes, causal inference is a very difficult philosophical problem. So we biologists must solve such problems in our daily empirical research. But this is my opinion. phylogenetic research maybe not in causal inference, but pattern inference, because wait for a moment. Because we tend to understand phylogenetic trees in a causal type it is causal form, but it is my opinion that such phylogenetic trees may not be in causal form, because this is a pattern which represents the distribution of characters. So this is not a solution for you, but I can find any good answer for you.
Thank you.
Okay. Now next. Yeah.
Hi, I'm Rudy Rucker from San Jose State, and I was wondering what these days the best idea of the tree of life is. It would seem like, I'm not a biologist, but it seems like I keep reading about people comparing DNA, common DNA that species have, and using it as a way of going back. So I wonder, is there some one best tree that's online right now or something like that? Is that what you're working on? I wasn't clear. Are you doing research to find the best tree? It seems like you could do computer searches, but it's intractably large searches. That's the point you made. But it seems like with the DNA, there might be some converging on a better tree.
I think using DNA sequence, we have a convergent good solutions. Okay, that yes, that may be true. But my stance is that such best solution need not be true in historical sense. So our abductive inference must contend that we have a best solutions at a time point, and tomorrow we have another solution. So that is the fate.
Can I ask one more question?
Yeah.
The idea of abduction, I'm interested I'm a logician, so I like the idea of a new kind of logic, and I'm having trouble seeing the distinction between induction and abduction.
Yes.
Because induction, I see phenomena and I try to make up an explanation, and abduction sounds very similar. So what's the difference?
Okay, wait a moment. I understand abductive inference as in this four-step procedures. So the most important point is the third. So in this case, a hypothesis H is the best among other alternative hypotheses. So in this comparative context, or context dependency is characterizes abductive inference, which is not shared by inductive inference. So choosing among competing hypotheses is the most important point which characterizes abduction.
Okay. Now, yeah, please.
Hi, I'm Akio Kanai, a molecular biologist at Keio University. Since I'm a molecular biologist, I just ask more practical questions. What do you think are the most important factors to make the best trees? Like is it the DNA or the protein sequence, the comparison of whole genomic sequence?
My answer is, as the case may be, because of course, molecular sequence has high information content. But morphological characteristics or any other non-molecular characteristics may be useful for estimating at least some part of phylogenic trees, which can't be solved by molecular sequence.
And what's your strategy to make your trees?
At present, I must use molecular sequence there. Okay.
Maybe molecular sequence is very important, but
Yeah.
like he said, some genes are very mixed up, like horizontal transfer.
Yeah.
So that I think that my opinion that to compare all set of the sequence to to generate some poison between the species.
Yes, of course.
Very
Different
important.
genes have different history. So in this case, there may be inconsistencies between gene trees.
Okay. Now still have 10 minutes. Yeah.
Good morning. My name is Hirota Naka from ATR Neuroscience Laboratory. So I'd like to know the practical procedure about the inference of a dipole tree on a tree of life. So in that procedure, so you are just presenting.
Yeah.
So D is existing species or fossil species on Earth, and we want to estimate the structure tree. So H is hypothesis, H is the structure tree. So maybe you can use a Bayesian inference, and I'd like to know what kind of prior probability you assume.
Bayesian probability or Bayesian prior is a very difficult problem because I don't want to use Bayesian methods in phylogenic analysis because we had perhaps non-realistic models for prior distribution for phylogenic traits. So I prefer Bayesian analysis to estimate for the relationships.
So let me ask another question. So if you don't assume any prior information,
Yeah.
so you need to have a model about the likelihood. So in the second procedure, you need the likelihood model. And what kind of likelihood model do you assume?
Okay, in this case, we assume, say, uniform prior. Uniform distribution of prior.
Right. But the likelihood, you need a likelihood model. So what kind of likelihood model do you assume? That's my question.
So, when I explain this kind of abductive inference, I don't know any particular model for schemes for this procedure because this is a more general kind of estimation procedure. So that doesn't depend on any likelihood or Bayesian models in this case.
Okay. Yeah.
May I ask your definition of evolution? What do you think evolution is?
My definition of evolution is the connection, historical connection between ancestor and descendant.
Is it like somewhat Lamarckian evolution? Or?
No. Not at all.
Okay, thank you so much.
Okay. Now you have been receiving many questions about the difference between abduction and induction. So let me ask only one question finally. Well, I'm from physics, and in theory of phenomenological theory, it's exactly corresponds to this process. For instance, there are several kinds of different phenomenological theories, and most one is best corresponding to or explained in the experimental facts also. And one phenomenological theory will be chosen. So in that sense, it's also answering your question that for me, at least for me, it's just a not so strong difference between abduction
yes,
and induction in physical field.
Yes, of course, abduction is weak inference schemes, not strong. But in historical or evolutionary biology, such weak inference is the best choice for our research program.
Okay. So let me appreciate once more. Thank you very much.